some troublemakers here.
Right, recording. Okay, it's recording. All right, so we'll begin now. And a couple of things. Uh, I'm gonna keep my video on because I might have to like show some hand gestures to show some geometry or something, or might have to show some drawings on the paper. And I might not be looking directly at the camera because I have two screens, so don't worry about that. All right. So, to begin with, what we'll be talking about today is vision. In a sense, how can we use visual information and images to gain information, and after gaining that information, be able to take decisions based on that information. So, uh, essentially, we will be dealing with a couple of not couple two basic broad domains: detection and pose estimation. Detection, in easy words, is just detecting what we see and what it is, and pose estimation is essentially where is it in the environment, right? So based on these two things, the next question that we have is that why do we want to do this and what will it help in? So this is actually what ultimately we will be aiming at. This is just like a quick overview of what at the end you can expect. So suppose that you have two cars racing on a race line on a racetrack. So it would be a very good information stored that you have the understanding of where the car is ahead of you, which you are racing against. And for example, in this, you know that where is this car with respect to yourself, and also more than that, if you have an understanding of where the car will be in the future, depending upon some heuristics or dynamics, or uh, maybe even a learned network. So, for example, in this image, I'm seeing the car here and I'm predicting the poses of that car based on some heuristics and some assumptions that we'll talk about in a while. And using this information, can anyone tell me, just so that we know that people are here and listening, that where can we use this information? How can this information be useful? Anybody has any ideas? Anyone? Okay. Okay. Uh, all right. I'm assuming either people are okay. No are. All right. So essentially, having this information gives us an edge over uh, not having this information, because if we do have this information, the path that we will plan around these poses would be safer and would be more robust. For now, let's just keep that in mind, that we have more information so that the decisions that we will take would be more accurate, or would be more I want to say would be more decisive. We'll have more grounding over what we are about to do, right? So why do we need that? And people, this is actually an ongoing research problem, the problem of prediction, predicting where somebody would be in a while, few seconds into the future. And the question also is, do we need to do that, which we just talked about in the past slide. So for example, in this picture, we see that there are pedestrians, and we want to know where the pedestrian would be a few seconds into the future. If we do have this information, and I'm seeing this pedestrian here, and I have the information that okay, in the next 2 seconds, this pedestrian will possibly, with some amount of probability, come at this location, I can then decide to brake, to slow down, or to just honk my horn. So these decision making processes are no longer based on where the object is currently, but also based on where the object will be in the future. So these are a couple of approaches that are currently being used to perform this prediction. The first approach, which is discriminative, essentially it does not. So, so in order to predict, what will you predict? You will either recreate the situation, the entire situation, a few seconds in the future, or you will try to predict only the action of the object or what you're seeing without recreating the scenario. Discriminative approaches take the second approach. That is, they do not recreate the entire situation, the entire environment around the vehicle. They just predict what they are seeing and what its action would be. Right. So this is a quick video in which they show Mobileye, which is an Intel's autonomous driving uh, branch. They are working on software solutions for driverless vehicles, and they perform predictions based on objects or not recreating the scenes, right? So they see something, and this does not have a lot of information of what is going on under the hood. But yeah, that's the discriminative approach. The paper which goes with this is here, if anybody wants to take a look at it. On the other hand, the generative approach works on the entire environment that the vehicle is seeing. For example, this is a very, very, very good, um, it's a very intuitive understanding of what goes on in a. Okay, Soumya. I am playing the video, but I'm playing it inset. I'm not playing it completely, like in the full screen. Is that okay? Also, like instead of typing in the text, you might want to like just switch on your mic and speak because I might miss a text.
Yeah, I didn't see it being played actually at all.
Do you see it now on the screen?
hmm I'm not sure if others can see it.
Do you see the slide titled Two Approaches?
Yeah. I see the slide, but nothing being played.
I see. Okay. Pin the slides. How do I pin the slides? Um, this is strange. Can nobody else see the video being played?
I can see it.
I got you.
I can see it.
Yeah, I can
Oh,
see
okay.
it.
I've pinned the slides now. Thanks.
Okay. All right. So, like just for Soumya, essentially, do you see in the videos you see a bunch of boxes and you see lines which look like roads. So what Waymo did was essentially they took all the sensor information, all the sensor data, and they created a very simplified visualization of the environment around it. The ego car is green. All the obstacle vehicles are yellow. We have stop signs which are red. We have road markings. We have buildings and everything. And this entire environment that Waymo has created using its sensor information, it can then evolve this world into the future and predict as an entire environment where everything else will be, right? So
hmm
is does that make sense of like how these two things are different, generative approaches and predictive approaches?
Yeah.
Okay, any questions so far? All right, no. Cool. So let's move on. Then, what are the methods that we can use to perform these predictions? The first thought that should, might come to everyone's mind is deep learning. This is prediction. We have been learning and thinking and hearing about predicting things using machine learning and deep learning approaches, right? But even then, the deep learning approaches even rely a lot on a lot of conventional algorithms, such as particle filters and Bayesian algorithms and Bayesian equations, such as in this image on the right. Uh, okay, I don't think you guys can see my cursor either. Can you see my cursor? Yeah. Right.
In the slides drop
Yeah.
like bar,
Oh,
there's a thing that looks like a little red dot that's the pointer.
pointer.
If you click the pointer,
Gotcha.
then yeah,
Yeah,
there you go.
saw it. Okay.
No problem.
So, yeah, so in this image, if you can see, there are a bunch of, so this is the ego vehicle, right? And it's seeing a bunch of vehicles. So what it has done, it has assumed that all the vehicles um, I will approximate them by a box, and then using something like a particle filter, I will try to estimate and predict its position, because knowing the assumption of a box, I can then run algorithms such as particle filter and try to match, or scan matching, and try to match that shape to what I'm seeing. And in that process, also perform pose estimation and or prediction, right? So deep learning is something that you should look at, but it's not the only thing that might work, right? So these approaches we will not be covering a lot, because we will try to keep it simple, and so that it can be covered in class, and it is an ongoing research problem. So if you want to look into it, we can like talk on the side or approach it differently. Okay, so the
Yeah,
topics that we will cover today.
let me jump in, Sid. So
Sure.
the deep learning based approach is good options for projects. We'll talk more about it in a week or so. For class, we're just trying to get the basics, as Sid said. So don't want you to feel like we're not going to cover it. It'll be a choose your own adventure situation, though. So
Okay. So, the topics that we will cover today would be, I believe some of you would have already gone through these things in CIS 521 or 520, meme 620, or yeah, that's about it. So, we'll cover single view geometry, we will cover pose estimation, we'll cover how and what is homography and how it is used for pose estimation, and finally we'll cover how to predict this, how to perform trajectory prediction. The last part is not deep learning, just to put it out there right now, but we have a solution that works in our situation, which we'll be looking at to give you a feel of what it does. So for single view geometry, the very first thing that we should start off from is the pinhole camera model. um, Very basic, very fundamental. Few of you might have done this in your high schools, but you create a very small pinhole in the box, and you throw you light up a bulb inside, and you pass the light through something, and it will show up inverted, right? So that's happens because of diffraction of light, simple physics, Newtonian. So base the entire geometrical vision stems from this simple concept of diffraction of light, of how light diffracts through lenses, right? So the pinhole camera model works on the, of course, works. A lens also works the same way as a pinhole camera model would. So essentially, we'll have a camera center, we will have the image plane where we will see the object that we are seeing, and we will have the object itself. So in the previous slide, we mentioned that the image is inverted. We don't want the image to be inverted. So what we do is we place the image plane in front of the camera center instead of behind the camera center. So in case of a simple ideal pinhole camera model, there is this hole, the image plane is behind it, the object is in front of it. In this situation, if we place the image plane in front of the object, in front of the camera center, we get an upright image. There's no inversion. So the properties of the image that we see depend upon the certain characteristics of the pinhole, or so to say, the lens itself. In the case of the lens, it's the focal length, right? So if I'm seeing an object which is, say, z distance away, and it is of height, say, y, so the height of the image itself will be Fy by z, and the distance itself will be formed at the focal length, that is the image plane, right? So basic physics, basic optical physics that we have learned in high school, it all goes there, and we stem off from that pinhole camera model and the lens model and go on to an actual camera, right? So we'll start with the actual camera. um, in a camera that a lot of us must have used, we have a number of components that we see, right? So let's talk about the components of the camera and how they go into creating the formulations that we will use. Before that, is there any questions that you have from the previous slides or before that? Or is this clear to everybody? Not Gator Curry, everybody. Okay. Alright, so moving on. So we have the lens, which is the external lens. We have the internal intrinsic lens, and we have the body itself, right? So, and what we are seeing is this nx in the world, and what we will get in the image is an x in the image. Essentially, x is a point in the world, and this small x is a point in the image, right? So we'll talk about these components, K, R, and T. L is more or less a lens also, so its properties will be similar to what the focal length, the distortion coefficients, and other things which the intrinsic camera parameter also have will be. So before we move on to this, we see an x here and we see an x here, but we also see a 1 right here in both the sides of the equation. Anybody has ideas why do we add a 1 at the bottom of this position that we are trying to see in the world?
To
Anyone?
accommodate translation. Homogeneous.
Right. You said that. Homogeneous transformations, yeah, because I moved on to the slide and it was visible there. Anyway, so, okay, so the next question I would have is that why do we do homogeneous transformations? Why is it important? People chime in.
You can do rotation and translation just by a matrix multiplication then.
Yes, that is true, but why can you do that? Like, why does adding 1 makes it easier? I mean, that's the effect. What's the cause? Anybody? Okay. So, yeah, go ahead.
It's because you're adding the translation vector is the fourth column, and so you're adding each component of the translation vector into the results. And that's what the 1 is doing. We're
Okay.
talking about the one on the right, not the one on the left.
Yeah,
Yeah.
that's correct. Okay, we're getting close.
Is it about the projective plane? Like which is at a distance 1?
Yes, that's the one on the left,
Mm-hmm.
right? Yeah, that's the
Yeah.
one on the left. Okay, that's closer. That's even closer. Good. So how about we look at it in something like this? Suppose that we want to move from 3 dimensions to 2 dimensions, right? Because our world is a 3-dimensional world, and the image itself is a 2-dimensional image, right? So what we want is that make our 2-dimensional plane, which is the image, into a 3-dimensional world, because, well, we are seeing a 3-dimensional world. So if we reduce a dimension itself, things would go wrong. So what we do is we say, all right, fine, I am seeing all the points in 3D, but all the points lie at a distance of 1 from my origin. So I create a plane, the image plane, at a distance of 1 from the origin and call it a day, right? So now all the worlds that are in 3D are still in 3D, right? That's how it helps us to make sure that we do not have a loss of dimensionality when we move from 3D to 2D or vice versa, right? Does that make sense to people? Questions? All right. So now let's take a look at all the parameters that we were talking about a couple of slides ago. The first parameter that we'll talk about is this K, which is internally inside the camera as a lens. So what we see is that if we go back to the pinhole model, and if we go back to the pinhole model, we saw it in a 2D plane, right? Like just one dimension, just finding out the y, and we know the focal length. So if we wanted to have both x and y components, we can do the same thing. We just do fx upon z and yf upon z, where z is the distance in this direction, focal length, right? So the equation that we had here, this one, if we try and make a similar one for x and y both, and we know that z is z because we made it constant for this image plane, we can have a matrix formulation like this. If you expand this matrix formulation, you'll get what? You'll get x dash is equal to fxc, y dash is equal to fyc, and you'll get z is equal to zc, right? Simple enough. So now we have this focal length, which is in the x direction, and in the y direction. More often than not, the focal length in the x and y both directions will be the same. There might be specific lenses where it's not, but it would be rare to come across them. Even if we do, it's just a matter of changing them here, right? Now, this is one component. Then we know that in the image plane, we work in the image plane, but in the world frame, we work in the world frame. So there's a difference in the units of measurements in the world and the units of measurements in the image. So we also need to take care of that. Then we also need to take care of the optical center, because the image, if you have worked with images in Python or C++ or just worked with images and computer vision, you would know that images are essentially matrices, and with matrices we begin counting from the top left corner, which is 0 0, and then go ahead column wise and row wise, right? So the columns towards the right, the rows to the bottom, and the optical center, however, will lie in the center of this matrix. So we need to take care of that. So we shift every pixel by the optical center, and then we divide it by the scaling factor, which relates the meters that we have in the world to the pixels that we have in the image plane, right? Is that clear to everyone? Because that was like 2 slides, good amount of information. Any questions? Okay. All right. Okay.
So the image center is always the optical center?
Optical center is the center of the camera lens. Image center may or may not be that. I will not say it's definitively that, because it depends a lot on the height and width of the image also, right?
Mm-hmm.
So not always it's not definitive that the image center is the optical center. Might be off by a bit. Also, things like distortion or skew might have an effect, right? So we have the scaling factor, we have the optical center shift. Any other questions?
Is R and C, are they points in the, like, what is R? I know that reflects the
R
columns and the rows.
Yes, they are pixel points.
Oh, okay.
Right. So anything that you see in the world, like if you see this top thing, right? So this will be some column C1 and some CX and some row RY, right? So CX RY comma CX will correlate to some meters in X and some meters in Y.
Okay.
Right. So that's that. Any other questions? Okay. So now if we place all of this together, right, we have SX, SY scaling, optical centers, and K is a distortion coefficient, right? We don't have to worry a lot about that. It's if the images are warped or skewed or distorted, it takes care of that, right? So if we put all of this together and then C expand it, we would get these same equations and the X dash and Y dash scaled by the focal length, right? Is that, I mean, this is a good practice. You can just like write down this equation, multiply it, expand it, find out all the equations for X, Y, and Z. The X, Y, and Z is in the 2D world, 2D image 2D plane, image 2D world, and this XC, YC, ZC is in the is what the camera is seeing, right? It's what the camera is seeing in the world. So essentially, do I have something to show this? Okay. So if this is the camera and I'm looking at this, so XC, YC, ZC is the position of this thing, and if the image plane is this, small x, small y, small z is at with z as 1, x and y is in this plane, just 2D. Right. Now, we just had a very strong assumption that we are saying that this 2D plane, essentially we do have a z, right? But what we just did was we said that fine, I'm gonna take z out and say like here, so I'm gonna take c out, and when I take c out, this x dash is actually x by z. So to make this one, to make that strong assumption that my image plane is only a unit distance from the optical center, but it's not like the ZC vanished, right? It's still there. So this leads us to an issue which we call as the scale ambiguity, right? If you multiply all of these things together with values, you'll still have a non-unit value here, z. But when we say that we are assuming that my image plane is a unit distance from the optical center, I have to take the z out, and only then I will get the correct x and y pixel values. So, but still this z is still there, right? This z is still there. So what do we do with this scale ambiguity? Because as we move down in the lectures, you'll realize that it's not like that we have the world coordinate frames and we're trying to see the pixel coordinate frames. We're trying to do the opposite thing. We have the pixel coordinates and we're trying to do find the world coordinates.
Is that world or camera coordinates?
I'm sorry, yeah, camera coordinates. Sorry, yeah, correction, that is the camera coordinate frame. That is essentially from the optical center of the camera where the object is. world coordinate frame would be somewhere in the world that you have assumed a coordinate frame, right? This is the camera coordinate frame. C, this one. Okay, and the pixel coordinate frame is this scaled by the unit distance of image plane. Right. Any other questions? Okay. So, scale ambiguity, right? To understand scale ambiguity, it's very simple. If I'm looking at a point P here from my optical center, and I say that, okay, fine, I'm seeing this image here and here, but what I don't know is that how far is that point P, because it could be y, which is this, can be equal to focal length into y by z, this by this y by z, or it can also be equal to y dash by z dash, which is essentially what congruency of triangles? No. Triangle similarity, yeah. By similarity of triangles, both of these equations hold, right? So for a given image y, of height y, I don't really know if the object is of height y dash lying at z dash, or is it an object y lying at, is it an object of height y lying at a distance of z? Right. This is a very important concept to understand, because this is one thing that needs to be solved. This is essentially what the entire pose estimation tries to solve, to make sure that we have the depth and the xy coordinates, and that depth is the more troublesome part of it. So is this clear to everybody? Okay. So this is scale ambiguity, and when we extrapolate it in our camera with x and y both, we call it the projective equivalence, right? Which essentially means that there can be more than one points which have the same image on the image plane. So P, this P, this P, all of these P's will have the same point on the image plane, right? So this is the projective equivalence. It's the same thing as scale ambiguity. It's just what we call it, or we talk about in terms of when we talk about a camera and images, right? So now that we have transformed our points from the camera frame to the image plane, the next thing that we need is transformation between the world frame and the camera frame, right? Going back, backtracking a bit and talking about the very first thing that we talked about, is that why are we doing all of this, is to understand where the object is that we are seeing, right? So where the object is that we are seeing depends upon is essentially this information, where in the world the object is, right? So what we want to know is that, fine, I went from my camera frame to my image plane, but ultimately what I want is the world frame coordinates. So there will be a transformation between the camera and the world itself too, because the camera, if we go back to our body, is this, right? So we also want this component. We just talked about the intrinsic parameters which lie inside the lens. We also need to understand the RNT, which is how does this transform to this, and thus we have the world, anything I'm seeing, where is it with respect to the entire camera of the world, right? So now we will talk about the CRW and TCW, which is transformation of rotation of the camera with respect to the world, or translation of the camera with respect to the world, right? Now, we put it all together and we see, and now these things are something that we will find out. This is actually what we will try and find. Don't worry a lot about like what's happening here, and this is not being explained a lot. This is what we will find in a few minutes. Okay. Now, putting it all together, we have the focal lengths, right, and the optical center and scalings, and we put them together in the K matrix, right, and then we multiply that with the translation rotation that we will get or try to find out, and that will take us from the world coordinate frame to the image plane plus this lambda, right, plus this lambda. Let's not just keep this lambda at the back of your head. It exists, and we will try to solve for it. Any other questions so far? Anyone? Any questions? I'll start asking questions now. Okay. Okay. So now, what are the variables that we are interested in this equations? Can anyone tell me?
R and T.
Okay. What else? Is there anything else that we don't know?
Lambda.
Right. Correct. Is there anything else? Okay, so I just had told that we will know these x and y pixel values because we are getting the image. How do you think we are getting these points? Anyone? No. Okay, so let's keep this at the back of the head that got to find this, got to find this, somehow have an information about this, and definitely have an information about this, right? So this leads us to pose estimation, which is essentially got to find this. The fundamental idea that we are trying to bring forth is that if we have knowledge of corresponding points, when I say corresponding points, you can try and remember what we did in scan matching. We tried to find corresponding points, right? Similarly, in this problem also, if we have corresponding points, if I know that a point 2 meters from this means 1 meter from this and 1 meter from this here is somewhere around 7,6 pixels from the center, or 23,17 from the top left corner, which is where the image coordinate origin lies. If I know that this 1,1 corresponds to 23,7 scale ambiguity, we will be able to find the transformation between this point and this thing, right? So that is what we want to know, that if this thing was mounted on my car, right, and I'm seeing this, where is my car with respect to this, or where is this with respect to my car? Okay, so what we have to do, we have to find the correspondences and we have to find the scale ambiguity. So in order to solve this, there are a bunch of linear algebra tricks and tips which we do, right? So this is one trick that is most frequently used while doing this, and if any of you have taken meme 620, this is picked up from there, and this is what is more often than not a very good place to start with when you're trying to perform geometrical vision computations, right? Okay, so let's take a look at this equations, right? Let's just omit the lambda sign for now because it was a scalar, so more more or less it will just scale this entire thing by some amount. It does not give us the accurate, correct RNT, but it will give us a scaled RNT maybe, right? Because it was just a scalar, so we can put a proportionality sign here, right? So then we move ahead and we see that we have this choice. Then we can make the world coordinate frame anywhere in the world, right? So whatever I'm seeing, I have the choice and the option of keeping things off at where we are in the world, right? So how about I keep this coordinate frame on the ground here, right? I keep the coordinate frame on the ground of what we are seeing and what we are interested in, right? Can anyone tell me why would I do that? Like, how does keeping the so just to make it more clear, the points that I'm interested in, the points that I'll be looking at are these dots, blue, red, green, yellow. And I've placed my world coordinate frame on this surface. How can this help? And the only points that I'm going to see here in this world are on the ground, and I've placed my coordinate frame itself on the ground. How does that help me? Anybody? I mean, what changes? Like if I shift it up, right? Or if I rotate it, something will change. But if I keep it solidly on the ground, lying on the surface, exactly, what special thing happens? Okay. What happens is that I can make the z0, right? Because it's on the ground and I'm saying that all the points that I'll be seeing at lie on the ground, I'm just going to make z0, right? Does that make sense? Does that make sense to everyone? Okay, I can't see, so I don't know, but I'm assuming that makes sense to everyone. Are there any questions about this? Okay, so we have made z0 that also allows us to make this row as null, because, well, it will all get multiplied with zeros and there'll be nothing there. So I'm going to make this row vanish, and I'm going to make this 0, and I'm going to vanish that 0. And what that leads us to is that this matrix, same x and y coordinate on the image plane, and we only have xy and xw and yw. As a matter of fact, it is not important that you keep z0. You can even keep z constant and you would have the same effect, because then again it would have no effect to the entire RNT, right? Because it will only be a scaling by scale value. So if my points that I'm interested in lie on the same plane, then we can perform this trick, right? So now we have the intrinsic camera parameters, the optical centers x0 and y0, the focal length, and we have the RNT, right? Now these two matrices combine together to form what we call the homography matrix. Homography it's not a term which is specific to just vision. It essentially means the transformation of some values from one frame to another frame, and this frame can just not be so like in control we perform transformations through mapping, right? So you can even term this think about this as mapping from one domain to another domain, right? So if we talk about SO3 and SO3, which we will not get into, but homography is a general term. That's what I'm trying to say. It's not just in vision, it's just a mapping, right? So in our case, we are mapping the world coordinate frames to the image plane coordinates, right? So what in these things, what do we know? We know that we will have the correspondence. So this and this and this are presumed known, and this thing, right? RNT, this is unknown, and this is what you want to find. The homography is also known to us. Now, try and understand that the homography does derive from this, but that does not mean that I have this. Homography comes because I multiply this here, and then I find these values, right? So this is unknown, the RNT are unknown, and what you want to find. And we know the correspondences somehow, and we know the intrinsic camera parameters because we made the camera ourselves. Does that make sense? Any questions? Okay. Now, so what we'll start working on with is the homography matrix. For now, just assume we know lambda, we have the correspondences. Specifically, just assume we have the correspondences, right? And we can calculate this homography matrix. So what do we do with this homography matrix, right? So we want to estimate the pose, the rotation, and the translation from the homography. Okay. Now, as I said, there can be interpretation of homography. In the vision world, we talk about mapping from the world to the image frame, or any other frame to be exact. It's just a mapping, right? And another way of interpreting is that, like I said, from the world frame to an image plane, or from one image plane to another image plane, right? So, like I said, it's a general term. It's just a mapping that you can calculate between any two frames. So even if it is the image planes of two different cameras, a homography will exist that can transform every point in this camera to every point in this camera. So don't think about homography as something only which goes from the world frame to the image plane. It can be from any frame to any frame, right? Now, the good thing about the homography that we are using, or maybe not the good thing, the constraint thing about the homography that we are using is that it's single view, right? So it's simply one camera. It's just seeing the world, and it has the information in the image forms. And what we need to find is the other point correspondences for the homography. We have to find the homography from the point correspondences, and from the homography we have to find the rotation and translation. Is that clear to everyone so far? Does anyone have any ideas of why we still have a scaling factor here? The W. Okay, because the same principles still apply, right? We are moving from one plane to another plane, but we don't know the depth ambiguity. Okay. Okay. So that is the path that we are going to take. Find out the homography from the point correspondences, and then find the translations and rotation matrices from the homography. Now we'll take care of the scale ambiguity, right? So if you remember, we had performed an assumption of keeping everything on one plane, all the points on one plane, and that helped us in solving this directly, right? So linear equations, this can be solved directly, and we have 9 parameters from the homography, and we have 1 parameter from the scale ambiguity that we need to find, right? But since this one row can be solved directly, we would need 4 point correspondences, 3 for the 3 linear constraints and 1 for the scale ambiguity. Can anyone tell me what are the 3 linear constraints that we're talking about here? Anybody? What are the linear constraints that we're talking about here? When we expand these matrices, we will have three linear equations. This got solved directly, and we'll have one more linear equation which can solve for this lambda I, right? So 4-point correspondences, 4 linear equations, right? Now we can do a bunch of linear algebra tricks, and ultimately what we'll come to is this, where xi, yi is x1, y1, the first point correspondences. Xi, yi is the world coordinate points. X dash I, y dash I are the image plane coordinates. And this h is the vector of unknown parameters. So we have entirely gotten rid of the lambda using the linear algebra tricks, because you're able to transform this entire problem into a set of three linear constraints and one scale constraint, right? So we're able to eliminate the scale, and we're able to get a formulation which only has point correspondences and a vector of 9 parameters. Is that clear so far? Questions, comments, advice, help? No. Okay. So now we have a formulation that if we have the point correspondences, I can find H. Now it does seem like that H lies in the null space of this matrix, of this 8 by 9 by okay, question. What will be the shape of this matrix? Oh, I would like somebody to tell me that.
8 by 9.
8 by 9, correct. So we have an 8 by 9 matrix. And is that clear to everyone that H seems to be lying on the null space of this matrix? I might be wrong. Okay. So it does seem to us that we have sort of a least squares problem in which H lies in the null space of this 8 by 9 matrix. So what we need to find is that is to find this null space, essentially, right? So this matrix, we have a system of linear equations, right? And we can use methods like Gauss elimination, right, to solve this system of linear equations. But there is a problem, is that we will have noise in the correspondences, right? Anybody can shed some light on why we would have noise in correspondences? This is something you also, I think, came across in scan matching. Anybody?
There might be outliers or points which may not exactly match to the point which we have.
Right. Essentially, it's simply put, like, we could have picked just 4 points, but if we did just pick some 4 points, who's to say that the correspondence is exact, right? So what do we do with that? Like, what are the solutions that we can have if in this case of a noisy scenario, that what can we do? Any ideas? And we can also like think about this in ways like the shape of the matrix. What is fixed? Is the row number fixed, or is the column number fixed? What changes if I change the row number or the column number? Or how can we change the number of rows and the number of columns? Right, that can help in this noise.
Take more correspondences, more rows.
Right, correct. So now that we know that essentially this is a set of linear equations, and this set of linear equations will give us some answer. if we took a bunch of correspondences rather than just four, the shape of the matrix will still be nine. Some r cross nine, right? So this matrix multiplication will still hold, and the null space will still be there. It would just become more accurate because now we have more information that we are basing this set of linear equations on. We just have more data which is being used to solve the set of linear equations. So we do that and we solve it in the sense of a least mean squares problem, right? This is the second trick that we use, that we consider this as a least mean squares problem, right?
If you take more than eight rows, you won't have a null space then, right?
Um, what do you mean?
Like
I
because
mean,
the matrix is 8 by 9 right now, we have a null space, but if it's more than 9 by 9, then we may not have.
so suppose it is 10 by 9, 10 rows, 9 columns. Then what will happen?
Like if there is an outlier, then we may not have the null space at all.
Yeah, I mean, then we will have a solution, but it will not be an accurate solution, right?
Yeah.
Yeah, so that's the case if we take 4 also. What helps in taking more points is that we might be
In 4,
getting.
there can't be an outlier because homography is 4 to 4.
Okay, so homography is 4 to 4, but we are trying to find the homography from the correspondences, right?
Mm-hmm.
So if we have if we had the homography, so we would be sure that there are no outliers from the homography that we are calculating. But we only have points, then are we guaranteed that the homography that we will get from it is exact in the sense of the correct correspondences? The 4 points that we have, do we know that, just simply put, do we know that do all of them actually lie on the same plane? And if they don't, even one of them don't, then will the homography that I get will be correct? It would be a homography, but it would not be the correct one that we want between these two frames. It would be from a slightly different frame, between two slightly different frames, right?
Yeah.
Right.
Okay.
So in order to beat that, what we try to do is we try to A, take a bunch of points, and B, we try to solve it in the sense of a least mean squares problem and use tricks like SVD, which is singular value decomposition. So just to reiterate, we have H1, H2, H3, which is the homography. Now, the first thought that comes in your mind seeing this equation is that if we just want this R and T, and we know for sure that we have the focal lengths and the optical centers, then who is stopping us from doing this, right? So again, it boils down to the same thing, that since the homography is not correct, who is to say that multiplying this with this will give us the correct result? So in this case, we can use like a bunch of algebra techniques. Some people are still doing research on this to make this more and more accurate. But some of the most common ones that are being used right now include like singular value decomposition, least mean square estimations, Ransacks, and SO3 constraint implementation. Can anyone tell me what is the SO3 constraint that we are talking about here? It's on the slide actually. Like, what is the SO3 constraint that helps us and in what way will it help us if I get, say, R1, R2, T gap? Suppose we did get R1, R2, T gap, right? What is the SO3 constraint that will help us give R3?
R1 cross R2.
Like, what is that? What is the constraint? What is R1
The
cross
rotation
R2?
should be orthogonal and determinant 1.
Right. The S, the rotation matrix. If any of you have taken geometrical vision 521, 23, I don't remember exactly. But the rotation matrices lie on the SO3 Lie space, and the specific property, which is actually in the name, it is the special orthogonal group 3, which means that the three columns of the matrix are orthogonal to each other, right? So if I have Rn and R2, I am absolutely sure that R3 will be perpendicular to both Rn and R2, and the way to take the perpendicular is to take the cross product. So I have R1, I have R2, and I can find R3, which is actually what we eliminated when we assumed that all the points lie on the same plane, right? So we did no harm by eliminating that R3 because we can ultimately find it, right? And to extend that, I'm talking about lying on the same plane. Now that plane can also be the y plane or the x plane. In that case, we would have eliminated either R1 or R2, but that would make no difference because we might have a different homography, right? But ultimately, when we want the three columns of the rotation vector, we can multiply either two and get the third one, right? So the SO3 constraint is a trick. Then we want to solve this in the mean sense of right. So we we have this constraint, and I know the homography, I know the intrinsic camera parameters. Ideally, this should work.
Um,
Yeah, question.
I have a question. Are we
Yeah.
sure that R1 cap and R2 cap are perpendicular to each other?
Ideally, they should be. If so, R1 cap and
But because
R2
of
cap
noise,
are
you're
not.
saying.
Yeah, they won't be perpendicular to each other, and hence R1 cap cross and R2 cap cross is also actually not exactly perpendicular to both R and R2, right? But again, we are trying to estimate. This is estimation. This is not an exact solution. So if we don't get in practice, so this is theory and this is the ideal scenario. When we code this, and because Shivangi, you were also in Beam 620, I remember we did this. We took R1 cross R2 by 2, right? You can
Right.
even take R1 cross R2 by 2. You just have to make sure that because the rotation matrices are not scaled, you can scale them. So if you divide them by something, it stays the same. It's a rotation matrix. So what you do is you try to get as close to the orthogonality as possible. It won't be exact.
How can you divide something like? Isn't there a condition that its determinant has to be 1?
Um, so the simple 2 cross 2 rotation matrix, right, of rotating about 90 degrees by about x-axis, right? If you divide that by 2 everywhere, right? Will it change? Will the rotation change? I might be wrong here, but yeah. Or even like forget about the rotation. Will the orthogonality change?
It will remain orthogonal, but it
Yeah.
won't be called rotation matrix then because it's scaled.
Okay, fair, right. So if the determinant is 1 after scaling, we will have the rotation matrix, and the values of the rotation matrix will give us the correct rotation,
Mm-hmm.
right? So yeah, so essentially we do want to make sure that our values are scaled such that determinant is 1 and they're orthogonal. So to ensure orthogonality or to get close to orthogonality as possible, we do this. We find two columns of the rotation matrix and we find the third one by the cross product of it. So this is the ideal situation. This will give us what we need, but there are better ways to do it. Single value decomposition, least mean square estimations, ransack, which we will not go too deep into. Solely the reason because you will not be coding it. What we will be using here is a library, and the library is based on the same assumptions that we just had and tried to understand, and the camera model and the single view geometry that we just talked about, right? So now we know that how do we get rid of the scale ambiguity. So what's next is that we have to find the point correspondences, right? That was the one thing that was remaining for us to calculate the homography, and from the homography calculate the rotation and translation by this. So how do we find the correspondences? In the world that you see, there are a bunch of interesting points that you have a certain fair amount of information of. These include things like vanishing points, parallel points, April tags. The thing that we will be talking about is April tags, right? And this is what we'll be using in our lab too. So we are now slowly shifting towards the lab and how to solve the problem that we will be bringing into the lab to give you a flavor of what detection and prediction looks like. So, April tags. April tags. Is there anybody who is not at all familiar with April tags? Just holler if you're not. Anyone? Cool. That's good. That's good. Let's work for me. So April tags, essentially, there are visual aids. They are very unique. Every single visual pattern is unique in every April tag. They have IDs. So for example, each of these April tags, they have a unique pattern in the shape of squares. And each of these patterns represents a particular ID. Say ID 1, ID 2, ID 3, 4, 5, right? And this is what we'll use in the lab. So how do they help us? They help us because these unique shapes with the unique IDs help us in differentiating them from other April tags. Then we know the dimensions of these blocks or the edges or the corners that these visual tags have. That helps us in having the information about the coordinate points, right? Now, if we kept this world coordinate at the corner on the surface of this April tag, we will essentially be doing the same thing, right? We would be creating a world environment in which all the z coordinates are 0, and x and y are known to us because the dimension of the blocks are known to us, right? We have a bunch of corner points that we can track, and for the corner points, if any of you have worked with edge detection, there are fast corner detections, Harris feature detection, and such feature detection algorithms that you can use to just find out the corners. And the corners we'll know where lie on this coordinate plane because we have chosen to keep this coordinate frame on the edge, on the surface of the April tag, right? So essentially what we made the assumption and what we talked about, given the unique ID and the unique shape and keeping the world coordinate frame on the surface of the April tag itself, we have a lot more information that we can use in order to find the homography and further the RNT, right? So we use something called the April tags library from Ross, and it essentially works very nicely, very smooth. It will take in a camera image and it will take in the camera info. The camera info is nothing but the intrinsic camera parameters, and it will give you the transform between what it's seeing, which is the April tag, and itself, right? It's very simple, very easy. It will take in the rectified image. It will take in the topic which contains the interesting camera parameters and resolution of the image, and it will output the position and the orientation of the April tag itself. For example, if you can see in this image, I don't know if it's big enough, but so this is the April tag that it's seeing, right? And it's able to find between the ID 0 April tag and the camera itself. That is the transformation, published as a TF transform, right? And under the hood, it is using the same thing, right, which we have talked about. So it would detect the April tag using certain kind of edge detection algorithms. In this case, it's the union find algorithm. It detects the April tag, then it finds the corners which we are interested in. The corners itself act as the features or the points of the word, and using things like Harris corner detection. And once you have the corners and the correspondences, you calculate the homography, estimate the pose. And once you have estimated the pose, you do things like hue transform or ransack to perform outlier rejection. So anybody who wants to shed some light on hue transform and ransack, which how can it be used here to perform outlier rejection? What outliers are we rejecting? Would we be rejecting possibly in this package? Anyone? Is anybody who's not at all familiar with ransack or hue transform? I can give a quick overview.
I am not very clear with hue transform.
Okay. Hue transform. Hue transform, how do I say this? It's actually more computationally intensive than ransack, so very less people use it. And even I'm not very thorough with it. Essentially, it tries to find. So what ransack does is that it finds the points which are closest to the best fit line, essentially. What hue transform does is that it draws lines through all the points, and then it does some computations to find the bands in which all the points lie. Matt, if you're around, you might.
I can do that. So of transform, basically you're just drawing lines. You can have ways to propose these lines, and basically each point that you're trying to match gets a vote. And by the end, when you have all the lines, basically if a line is close to a point is close to a line or on a line, that line will get one vote from that point. So you're kind of basically keeping a heat map of which line gets the most votes, and then that's how you find the best match line.
Okay.
It's kind of like similar to ransack, but the other way around. So you draw lines through all the points, and then you see that which line gets the most score.
So it's kind of like so ransack. You have based on your dimension of your model, you're drawing based on 3 points that you know, and then you try to find which one has the least outliers. But Huff transform is the other way, where you draw the lines randomly, or some sort of grid search, not from the points that you have, and then you check afterwards. So that's the main difference.
And it's not a random grid search, right?
I think there are different implementations. The one I've done before, it's a grid search where you just list out all the ranges of lines that you have. So basically, if it's a 2D line, you can basically write it out in one equation. You'll have a rise and the intersect with the y-axis. So that's the 2 numbers that you'll tweak to find basically all lines in a 2D plane, and then you do grid search on that.
All right. So essentially, what all we have learned so far and seen so far, the April tag does the same things. underneath its repository, plus some other things before and after the entire computer vision computation to make it robust. Right. So the second part, so now we have covered that we have taken care of the scale ambiguity, we have taken care of the correspondences, and all of these things are put together in this April tag repository, which you will be using, right? So now, so far so good. We know that we have an understanding of where the object is, the April tag in our case, with respect to the camera, how far it is, and what orientation is it. Now, the second thing that we initially said we would talk about is prediction, right? Is that if I know in the current timestamp where the April tag is, can I predict where it will be, say 10 seconds in the future, right? So that's where we talk about predicting the obstacle vehicle's trajectory, right? So in our case, we have a very specific solution, which is specific to our situation of racing, F1TENTH racing. And what we assume here is that both the vehicles, they will follow the trajectory of the track, right? In the case of the world, it would be, say, the line, what are those called? The center lines or the lane markings, right? In our case, it would be, in all probability, the center line of the track or the race line of the track, right? So if we say that more often than not, what we do is the pure pursuit trajectory, which is the trajectory that we have found from the map. And we say that, fine, I am more than confident that what I'm seeing is also racing against me. So it will also follow the same path, same track that I will, not the same path, the same track that I will, confined by these walls. So more or less, it's gonna follow this pure pursuit trajectory, right? And this is equivalent to the cars following the lane markings of the road. So taking that assumption, what can we do? We have two options, right? So in this case, when I'm seeing the vehicle and it's straight, right, and that's fine, we are going to go straight. But there's no stopping this vehicle, although the assumption states it, there's no stopping this vehicle from taking a left or right turn, right? So we can have two scenarios. The vehicle can go straight as it is oriented, or the vehicle can turn as the pure pursuit path is turning. So, for example, at the turns, the pure pursuit path turns, but the vehicle might not in the same instant that it is seeing it. It might later, it might before. But in the current instance, we can never be absolutely sure as to if the path taken will be the pure pursuit one or it will be straight ahead as it is oriented right now, currently, right? So my question is, which of these options should we choose? Should we assume when we see the vehicle that it is oriented in this particular direction and hence it will go in this particular direction only, straight ahead? Or do we assume that it will turn and try to follow the pure pursuit path? So if my pure pursuit path is like this and my vehicle is like this, will it go straight or will it try and go towards the pure pursuit path? Which option do you think we should choose? You can have a vote if you want, but it will be good to hear what people think. Which option should we choose? Anybody?
The pure pursuit one seems to be a little bit more intelligent than just the linear model.
Okay.
But linear model seems more general than pure pursuit. Like, if it was something outside of this class.
That's true too. But if we are just talking about the racetrack, and say even if the pure pursuit model, pure pursuit path is here, and my vehicle is here, Do you think that should we assume that it will immediately start turning? Should it take some time and start turning? Because we do not essentially have the understanding of the dynamics or the steering dynamics of the other vehicle, right? We don't know the decision making process of the vehicle in the front is that I will not turn, I will stay parallel to the pay pursuit line, I will only turn when the pay pursuit vehicle turns. Anybody else has any thoughts which option would be better?
I'll chime in. Is there maybe another option that you could choose? So I've heard we like linear because it's general. We don't like peer pursuit because it assumes something about the path that the vehicle is going to take. Could you generalize peer pursuit? And bonus points if you can think of a framework that would make sense for that, and on the theory lines.
Anyone?
Has anybody said when the linear model wouldn't work specifically?
Yeah.
So I'll talk since I think it's difficult for people to unmute. Linear model won't work when you're going around a corner, right? When you have to change the direction of the steering. So if you want to predict 2-3 seconds in advance, linear is not going to cut it. The pure pursuit version, right, has a very strong prior about what a good path around the track is. A generalized version of this might be to run RT or RT star or model predictive control instead of pure pursuit. So I would say that solutions along those lines like RT star MPC would fall within the framework of game theory. So you could look at iterated best response. So you say, what would they do if I did this? What is the best possible thing they could do? So that would make it more general, assuming that the other agent is somewhat rational. And so, yeah, I guess this third option is something you could be thinking about for your project after we do the RT and model predictive control lectures.
Okay, so I guess I'm gonna go ahead and talk. Right. So, like Matt said, like what would be a good generalizable pure pursuit model, right? So instead of choosing one, how about that we generalize pure pursuit and we choose both? So a good way to do this was to understand how a vehicle in all probability would behave. Intuitively, if you think about it, in the current times instance, the vehicle more often than not would move according to the linear model, but in all possibility, it would try and follow the pure pursuit path as time evolves, right? So if it's more like inertia, right? So if I'm currently in a current state, I would try and be in that state. But if somebody is forcing me, which is the pure pursuit path, to be in its state, I would eventually go into that state. But at the current time instance, I would try to be in my state only, right? So if that is intuitively correct, what we can do is we can take a weighted path over the time horizon, which is say 10 seconds, and we choose that our linear model will work closer to the time zero, and further down the time, as time evolves, we will try and take the pure pursuit path. Does that make sense? Right. So having this intuition, we can actually formulate this in the form of an equation, right? So having a weight alpha, right, and saying that fine, with this weight alpha, I'm going to have an exponential component to it, and I'm going to weight this, right, in a way that alpha linear model prediction plus 1 minus alpha pure pursuit model prediction, right? And I'm gonna have an exponent component over it. The sum of this is 1. So suppose that if we weigh alpha to be 0, right, we will have entirely pure pursuit model. And if we weigh alpha to be 1, we will have entirely linear model. So, and this I is equal to 0 to n is essentially the time steps. So we can get 10 time steps, but these we will get the states, the xn, the states for the 10 time steps, but these 10 time steps will not have only linear model prediction or pure pursuit model prediction. They will be in the initial times, as you have weighed them, they will be linear model predictions first, and then as time goes on, they will be pure pursuit model predictions, where I is the time step of where you're going on. So when I becomes n, which is the highest, we will have very less weighting to the linear model prediction and very high weighting for the pure pursuit model prediction. But initially, when I is 0, alpha is 1, we have entirely the linear model prediction. Is that clear to anyone? Are there questions for this?
So it's not completely clear to me. So you're saying the value of alpha changes as I increases to n, or is that I like an exponent power? I'm not sure.
So suppose alpha is 0.5, I'm saying equal weighting, right? Now I'm saying that I started from 0, 0.5 raised to the power 0 is 1, right? And this is 0, I think. Oh, okay, I see what I did. So I of a 0, 1, 0.5. Yeah, and this again will be 0.5 raised to the power 0. So we have equal weighting. Now
I think it should be 1 minus alpha power I.
I don't think so. So then you will not have equal weighting, right?
You will have it at time 1.
I think I just changed it. Okay, at time 1, suppose you have equal weighting, right? Oh yes, you're right. It should be alpha raised to the power I. I corrected it 2 hours ago. Never mind, it didn't show up. So yeah, so if it is alpha raised to the power, actually I can just like very quick change this to be, give me 1 second. Yeah, so if it was alpha raised to the power I instead of 1 minus alpha raised to the power I, we would have, as I increases, we would have the value of alpha decreasing because alpha has to be between 0 and 1. So what will happen is that as I increases, we would have lesser weightage on the linear model and more weightage on the pure pursuit model because alpha is decreasing as I is increasing. How do I save this? Does that make sense to everybody? Shivangi, was that clear to you?
Yeah, that's all my doubt. Yeah, thanks.
I'm just gonna change this real quick. I actually changed that and that did not show up somehow. Yeah, there it is. Yeah, there it is. Right. I'm gonna stop sharing this and present. And I'm going to stop presenting. Yep, did not show up before. So that's the correct one. Does this make sense? So if alpha is a value 0.5, right? And as we go ahead with time, with I increasing from 0 to n, okay, as I increases, alpha will keep decreasing because it's in decimal, right? So if alpha keeps decreasing as I increases, I will have more weightage to pure pursuit model because 1 minus something which is getting smaller, and it will have less weightage on the linear model prediction because it will have, because as this is increasing, the I is increasing, alpha raised to power I will start decreasing. So is that clear to everyone now? Questions, comments? Yeah, sorry about that. I don't know how that did not show up in the changes. Right, so I think for today we have got through how do we predict, how do we, before predicting, estimate where it is, and based on where it is, we predict where it will go, right? So that's all we had to talk about for today. If there are any questions, we can talk more, or if there are any other previous lab questions, we can talk about those.
Yes, I think what will be useful is if each person who's on the call now, before you leave the call, just say if you have questions or not, and then if you don't have questions, then you can leave the call. But just talk to us once before that, and so you can go in just in the order of the first names that are listed here. Just say that. You can just speak up also if you can, then that's easier also for us. Yeah, so for projects, we'll give you the guidelines on Monday. So in a week's time. So this week we're just getting restarted, and we'll have this lecture on computer vision. We'll start the projects from next week. We'll as we put the material for the projects together, we'll give you post some guidelines hopefully later this week. But the project discussion is for Monday. As I mentioned at the beginning of the call, what will be useful is each of you send us a note saying that you're interested in what type of project, or if you have a project idea in mind, and that will help us also tailor the next Monday's lecture to suit that, right? So, and we are also trying to see whether we can have like some kind of virtual um, environment for computer vision style projects up and running for you in Unreal Engine. And so we'll also provide that update on Monday. Yeah, regarding this deadline, Siddharth, do you know what is
RRT's deadline?
Yeah, because
yeah, I think it's 30th.
Whatever is the deadline on the calendar, we should just stick to our calendar that I posted.
Okay.
The link I posted.
Excuse me. Will we have a 3D simulation environment?
We will let you know that information because we are working on it. We'll try to see whether we can get that working by next Monday.
Yeah.
So if it works out, then yeah, you will have a 3D environment to run your project in, and that's what we're trying to do. So for the final race, we'll also provide that information in 2 weeks' time. So our goal for the final race is to have some sort of an online bot race where you would be developing your own bots to race alongside. and we'll provide more information on that. Matt, Billy, if you want to chime in a little bit on that. So we're again working on that to get that up and running for you, and it's not confirmed yet, right? So we're just letting you know beforehand that that's our goal. So we don't want to cancel the race in any way, and we will have the race virtually, right? So we cannot meet to have this race. So there won't be a physical race for sure. So over to you, Matt and Billy.
Yeah. So. You guys are familiar with the simulator, I think. You've been using it extensively. The general thing that we're trying to put together is essentially a containerized version of it, for which you can submit your algorithms to our server. It would be evaluated and with times and information posted to a leaderboard. There's two stretch goals that the TAs are working on. One is to sanitize our Unreal Engine version of the MLab corridor for use in your projects. And the other is to take some research code that we did for an ICML submission, which supports multiple vehicles within the simulator, so that you guys can have head-to-head racing for the final race. As part of that, we synthesized about 160 very strong agents, which you would be able to race against. So there could be two components to that. One is just your solutions head-to-head and your solutions versus auto-generated adversaries. We'll have some more clarity on that next week. I think it's likely that both things will happen. We have the code, but it's not like battle tested like the simulator code. So you'll have to be our guinea pigs, I guess. Hopefully that sounds exciting. And I think we could share the link on archive for the head-to-head simulator, so you can see what we're proposing.
As for the peer pursuit race, I think we could still have it if you guys still want it, but it's going to be toward the end of the semester. It's not going to be anytime soon.
As a proxy, you could run your peer pursuit code in the simulator and package it up nicely. So this is where we're heading, is that there should be a GitHub that we can pull from to get your code. And there should be a script in your GitHub that is named according to your team name. And running the script should execute your peer pursuit code on, let's say, the MLab map. So if anybody has something like that ready to go as a test case, we can start trying to do the remote evaluations. It would be helpful to the TAs. Somebody wants to volunteer for that.
You mean just a script that executes the peer pursuit node?
Yeah. So I assume that you're running multiple nodes to accomplish peer pursuit. So the script should start up all your different nodes, like a launch file, perhaps, would be good. Right. The idea is to automate this process so that when you submit your GitHub repo, we get your submission and our system pulls your code and executes your agent. Is that clear?
Something like a bash script?
That's fine too. Yeah, it's not standardized yet. Just it would be useful for us to see what you have. Yeah, launch file or bash script.
And it creates the map of the simulator. Like, what do we already have the map? Are we assuming that we have the map and the points, or does it?
You already have